Welcome back. This is worked examples second session. Here we will do conversion of complex numbers from rectangular form to polar form. So let's take the example number 1. So this says convert z, which is equal to square root 2 minus j square root 2 to polar form. So let's see how we can do this one. So first we have to find the modulus of z, which is simply the square root of the real number and the imaginary number, square root of the addition of these two squares of these two. So that's square of that plus square of that. So that gives us square root of square root 2 is 2 plus the same there 2, so which is square root of 4, which is equal to 2. So the modulus is 2 there, and it's very important when you have to find the argument, you have to draw the Argand diagram, because otherwise you can't get the exact angle where the vector is and where the exact angle. Now let's take this number z is equal to square root 2 minus j square root 2, which is, you can see the real part is positive and the imaginary part is negative. So this is our negative j axis, that's our positive j axis, that's the positive real axis, that's the negative real axis. So if you take the square root to be somewhere there and negative square root on the j axis to be somewhere there, we know that our vector lies somewhere there. So we can see now the angle that we are interested in, this angle theta, is a negative angle, because the convention is that anti-clockwise direction is positive, this is positive direction, and that is negative direction. So let's find the angle first. So we know that this is square root 2 and that is square root 2. So tan theta is equal to square root 2 over square root 2. We don't have to really worry about this sign here, because we are taking only the magnitudes, because we know that it is in the last quadrant or the fourth quadrant. We use the signs only to find in which quadrant our vector or the phasor lies. So this is equal to 1 and theta is equal to tan inverse 1, which is 45 degrees. So now our complex number can be represented in polar form like this: 2, which is the modulus, and then 45, that is the argument, but here that is negative 45, because we measure it in the negative direction. So that is our answer. The rectangular form, which is square root 2 minus j square root 2, can be represented in polar form 2 angle negative 45. So let's move on to the second example. The second example given in your book is convert this z is equal to minus 25 plus j 25 to polar form. So we have to convert this to polar form. So let's take the magnitude of this. The magnitude of this is again square root of 25 squared plus 25 squared square root, which is 25 square root 2, which is 35.36. And let's find the argument. To find that, like I said earlier, we have to draw the Argand diagram and find exactly where the vector is, negative real axis and j and negative j. So in this sum, the real part is negative and the imaginary part is positive. So we have, shall we say, this 25 lies there, which is negative 25, but the imaginary one is positive, so shall we say it is somewhere there. So we will have again these are equal quantities, so we'll have this shall we say this angle is alpha, and tan alpha is this side upon that side, and that side is 25 and that side is 25. So tan alpha is simply 25 upon 25, and alpha is equal to, that is 1, and that is alpha is equal to 45 again. So tan alpha, alpha is equal to 45, but then we are not really interested in this angle, we are interested in that angle there from the positive real axis. So we know this whole angle from here to here is 180, therefore that is 180 minus 45, which is 135. So our complex number in polar form, the complex number that we initially took as negative 25 plus j 25, now we can represent it in polar form as 35.36 and angle 135. So that's the answer. So let's move on to the next one, number 3. Let's convert again the same conversion. Z is equal to negative 20 minus j 40 to polar form. So let's write the modulus, that is 20 squared plus 40 squared square root, which is 44.72, and then let's find where the actual phasor is, or the vector is. So we can see this is negative and that is negative, that means both real part and the imaginary part are negative, so it should lie in the third quadrant. That's the negative j axis, that's the negative real axis, that's the positive j, that's the positive real axis. So if we take this part, say somewhere there 20, right, which is negative, and shall we take approximately double that because it's 40j, so negative 40 there. So our vector will be somewhere there, and let's take this angle as say phi, and we know tan phi is this side upon that side, so tan phi is equal to 40 over 20 because this side is 40 and that side is 20. Don't worry about the sign because we are interested only in the magnitude there, because we already know that the vector lies in this quadrant, so which is equal to 2, and phi is equal to tan inverse 2, which gives us 63.4. and now we have to find how we can represent this, because we are starting from the positive real axis, and if we go counterclockwise it is positive, and if we go clockwise it is negative. So we know this whole angle is 180, and now this is 63.4. so what we are interested in this angle here, what we are interested in this angle there, which is 180 degrees minus 63.4, which is equal to, so what the angle that we are interested is 180 minus 63.4, 180 minus 63.4, which is 116.6, and that is in the negative direction. So our answer will be Z is equal to the magnitude earlier we found, that is 44.72. so modulus is 44.72, and the angle is negative 116.6. so that's the answer. So here you have to be very careful. We use our knowledge to find in which quadrant it lies, and then we have to calculate the angle. So in this direction if you go it is negative, in this direction if you go positive. So let's go to the next sum, which is number 4. That's Z is equal to 50 minus J 15, and we have to convert this into polar form, right? Convert to polar form. So say Z modulus is equal to 50 squared plus 15 squared square root, which I will write straight away as 52.2. and let's find out the vector in which quadrant it lies. So you know that's positive j, that's negative j, and that's positive real axis, and that's negative real axis. And you can see this 50 is positive and imaginary part is negative. So this imaginary part will be somewhere there, say minus 15, and this one is positive, that's say 50. So our number will be somewhere there. So this angle, shall we say, that is theta, and that tan theta is equal to 15 over 50, and theta will be tan inverse 15 over 50, which will say write it like that, 15 over 50, which is equal to 16.7 degrees. So that gives us the complex number Z is equal to 52.2 and angle negative 16.7, because we are measuring in clockwise direction, always negative. That's the negative direction and that's the positive direction. So that's the answer. And finally, let's take the conversion from polar to rectangular. Convert, I will take a example in your book, or I will take a general example. Shall we say, I'll take a general example, say convert say 50 and angle say 30. So this is the vector and that's the modulus there, and that's the argument. So let's convert this vector to rectangular form. So we know that if you have a complex number like this, right, that's the 50 is our modulus, and the argument is arg is equal to 30. So what we can do is we can we know that it will be something like this. This is 50 and this angle is 30. That's our positive real axis, and that's the positive j axis and negative j axis and negative real axis. The modulus here is 50, so this will be 50 cos 30, and this will be 50 sin 30. So it's just a matter of finding this and that. Oh, that is our x coordinate and that's the y coordinate or the imaginary axis coordinate. So that will be our answer. So we can write it like this: 50 cos 30 plus j 50 sin 30. So let's find this with our using our calculator. So 30 cos will be 0.866, and when you multiply by 50 you get 43.3. So that is 43.3 plus j, and 30 sine, that's 0.5 times 50 will give us 25, j 25. So that's the final answer. So we get our complex number. When you convert it from polar form, that's the polar form, that's the rectangular form. Of course, we go through this intermediate step of trigonometric form to arrive at this. So this is quite easy compared to the other conversion, that is converting from rectangular form back to the polar form. If you need, we can do another example. Or I think since you can find angles, cos and sine using your calculator very easily, this will be sufficient.